mathematical and physical behavior of equations. So first to define different equations. So what is ODE and PDE we will discuss first. So what is ODE? ODE generally means ordinary differential equations. Ordinary differential equations. In ordinary differential equations, only which contains function and derivative of only one single variable. So in ODE, uh, only a function and it's a single variable, or let's suppose there will be only x or y, and there will be derivative with respect to x or y. So in ODE, equation contains functions and derivatives of one single variable. So in PDE partial differential equations, so it contains function and derivatives of several independent variables. So the difference basically ODE derivatives of only one single variable and PDE derivatives of several independent variables. Now moving towards linear differential equation and nonlinear. In linear contains product of dependent variable and its derivative. So in linear variable does not contain product of variable and its derivative. So, and a non-linear differential equation, it contains the product of derivative dependent variable and its derivative. So individual solutions to such equations can be superimposed, and individual solutions to these equations cannot be superimposed. So when I am talking about linear differential equation, it doesn't contain product of dependent variable and its derivative, while in non-linear it contains the product of dependent variable and its derivative. Now, the order of differential equation represents the highest order of a derivative. So the order of differential equation represents the higher order of differential derivative and not that of the independent variable appearing in it. So we discussed mainly three different types or four different types. First is ODE, or ordinary differential equation, then PDE, that is partial differential equation, then linear differential equation and non-linear differential equation. Now moving forward. Now, the mathematical behavior. So first to erase all this text, it depends on that the we have to erase all this. Now, depending the mathematical behavior of PDE. Now the mathematical behavior of PDE can be either elliptical, parabolic, or hyperbolic. So the mathematical behavior of PDE are of three types: elliptical, parabolic, and hyperbolic. And the basically the knowledge of mathematical behavior for a particle problem is crucial, important in selecting the appropriate numerical solution algorithm. And this is the mathematical behavior. And now the physical behavior. So physical behavior, we have equilibrium problems, we have marching problems, and we have eigenvalue problems. So in mathematical behavior, a PDE can either be elliptical, parabolic, hyperbolic, but when we are talking about physical behavior, it must be equilibrium problems, marching problems, and eigenvalue problems. Now, moving further. Now, Navier-Stokes equations basically are the second order and nonlinear PDEs in a four independent variables. So, when we are talking about differential equations, Mainly they are classified as hyperbolic, parabolic, or elliptical, or sometime mixed type. So for example, I am taking an equation that a1 del u by del x plus b1 del u by del y plus c1 equals to f1, and these two are equations. If u and v represent a continuous velocity field through the xy plane, the derivative of u and v are finite values at this given point. So I am talking about these two equations. So first, what is Cramer rule? So consider any point in the xy plane, such as a point P. This is point P in xy plane. Let us seek the lines or directions through this point. If it exists along the derivatives of u and v are indeterminate and across which may be discontinuous. These special lines that we are seeking are known as characteristic curves. So uh, this is my AB line and this is BC, CD. The points of intersection is the point P, and a characteristic curve that F and E is the mainly depends and the direction and the lines of magnitude of the force to the point exist. For example, in this case, along the derivatives of u and v are indeterminate and across which when they are across they may be considered as discontinuous. So to find such lines, so I am talking about these lines, these characteristic curves. Now I am looking to find del u by del x for this characteristic curve. So this del u equals to du equals to del u by del x dx plus del u by del y equals to this, and this is equals to this. Now the four equations. Equation number 1 is this, 2 is this, 3 and 4. Put them in a matrix notation form. So a1 b1 c1 equals this one. Now for 3, that d depends on du by dx. Du by dx is dx, and du by dy is dy, and no dv by dx, and so it must be 0 0. Now dv by dx equals to dx, and dv by dy equals to dy. In case is 0 0 because no du by dx and du by dy. They are equals to f1, f2, and in this case du and dy. So put them in matrix notation. So a1 b1 c1 is my a, and the b basically this is my a1, and the b matrix is uh, converting or interchanging this row with this one. So a1 a2 dx 0 is replaced by f1 f2 du dv. This new matrix is denoted by b. So the for solution we have to find du by dx. So du by dx equals to matrix b, that is its determinant and determinant of matrix A. So for Cramer rule, what happens if we choose to move in a direction away from point P such that A in the above equation is 0? Such characteristics line indeed do exist and we can find by setting. So in this case, put, put the derivative equals to 0. So this a1 a2 dx, this full matrix equals to 0. Now expand this whole determinant. Now after this we have moved towards the now a1 c1 c2 minus a2 c2, this must be equals to a, and this full value a1 d1 minus a2 d1 plus b1 c2 minus b2 c1 equals to b, and b1 d2 minus b2 d1 equals to c. Put this a b c in the equation. So we have find that this is a du by dx whole square minus plus b du by dx plus c equals to 0. So this du by dx must be equals to minus b plus minus under root b square minus 4ac divided by 2a. Now this term b square minus 4ac is of importance. So this must be equals to d. So d equals to b square minus 4ac. If b square minus 4ac, if d is greater than 0, so two real and distinct characteristics exist through each point. So this system is known as hyperbolic. If d equals to 0, it must be parabolic. And if d is less than 0, the characteristics lines are imaginary. The system is known as elliptical. In case of cone, for example, ax square plus bx square plus cy square plus dx plus ey plus f equals to 0. So b square minus 4ac is greater than 0 in case of hyperbolic, is equals to 0 for parabolic, and is less than 0 for elliptic. Now, the eigenvalue method. The eigenvalue method, basically I am focusing about these two, a1 and the same equation 1 and 2. F1 and F2 are 0 for simplicity. So first we have to replace F1 and F2, so it must be equals to 0. Now a vector or a new value, that is W equals to U and V. So first A1, C1, A2, C2. Just a minute. This A1, C1, A2, C2. This must be equals to du by dx, du by dx, dv by dx, and d. So this du and v basically is the function of w, or and the all are derivative with respect to x. So these four values must be the whole derivative of delta w by delta x. Now in second case, it's b1, d1, b2, d2. So its variables are u and v, so it's must be changing with respect to w, and the denominator must be changing with respect to y. So this is the full equation. Now put a1, a2, c1, c2 must be equals to k, and b1, b2, d1, and d2, this must be equals to m. So putting the value of km in the equation, so this must be replaced by this and this. So we have find this one, that k inverse m equals to this one. So k inverse m, this is the value of n. So replacing the value of n in this equation, so this is the whole, that with respect to w, a special vector, this is the value or a vector field with which changes with respect to u and v. So this is the n. So the eigenvalue of n determines the classification of the system. This n basically describe the classification of system. If the eigenvalues are all real, the equations are hyperbolic. If they are all complex, they are elliptic. If lambda equals to 0, lambda equals to infinity, the equations are parabolic. The eigenvalues may be a mix of both real and complex values. The mathematical behavior of such equations thus exhibits a mixed hyperbolic elliptic nature. So see the example 3.1 for the further, for Anderson book. You will be more clear about this lecture. So this is basically the end of the eigenvalue problems. So now the physical behavior of different type of equations. So when we are moving or talking about the physical behavior, each type of equations have a different mathematical behavior and which reflects the different physical behavior. In turn, this implies that a different computational method should be solved for equation associated with the different classifications. For the case of hyperbolic, in hyperbolic system, so first I have to draw the graph. This is my initial points A and B. So first it moved like this, and this there's a point of intersection, and there's also a point C. Okay, so this region, basically region 1, influenced by a point P, or it's known as region of influence. This region is known as region of influence. Region of influence. So this is point P. This line is left running characteristics, this line, and this line is right running characteristics. And this region, now this is the region 1 known as region of influence. Now the region 2, this is influenced by point C. Okay, this region is region 3, that is domain of dependence. So there are basically three regions. Region 1 is this one, R1, which is the influenced by a point P, and it's known as region of influence. This is influenced by point C. This is the domain of dependence. This is basically the hyperbolic equation or physical behavior of hyperbolic equation. Now, steady inviscid supersonic flow. In steady inviscid supersonic flow, the Euler equation hyperbolic when Mach number is greater than 1 and it's space marching. So when it moves with an velocity, there is a a b reference point. So there's a blow shock wave. This is a blow shock wave, and there's a point. Point is there. This is a point. It's rough left characteristic curve and right characteristic curve. When they are dealing with supersonic, there must be a wave generating in this part, that is D, and that is the point cutting at E. So this is E, D, and this is C and F. So basically, this is basically the modified form. First, the characteristic uh, surfaces. These are surface characteristics. This part is the surface characteristics. This is volume influenced at point P, and this is basically the initial values or initial data in XY plane upon which the P depends. So it depends basically on these three regions. Now, moving forward, unsteady inviscid flow. Euler equation subsonic or subsonic. Okay, time marching. And basically the previous, it's space marching. Steady inviscid supersonic flow is space marching, whereas the unsteady inviscid flow is time marching. This is also, there are A and B initial points. When they coincide, there's a point that is known as P, and the region of influence is now on the upper part that is moving towards y-axis. And I have t time, so it depends on time derivative, or with it changes with respect to time. This shows that it changes with respect to time. Now, parabolic equations. In parabolic equations, there are one real characteristics, region of influence, forward marching, and marching solutions. So initial data, boundary conditions are known, and, this is the region of influence. Steady boundary layers. Steady boundary layers are basically boundary layer equations. Marching technique basically starting from initial data at the nose of the point. Basically, starting at initial data at nose. So this is implicit flow outside the boundary layer and the boundary layer viscous flow. So when there is a flow, there must be a wall boundary and there's an outside edge boundary is there. Parabolized viscous flow. So for when I am taking the flow is supersonic, so this region is the shock wave, and this region is totally viscous shock layer. So I explain it again. When there is a velocity which is supersonic, so the layer this layer is basically due to shock waves, and this region thus made is known as totally viscous shock layer. So boundary layer equation not valid, and if all the viscous terms in that involve derivatives in the streamwise direction are neglected and the flow is assumed steady, we can get what are called parabolized Navier-Stokes equation. Uh, Parabolized Navier-Stokes equations are simpler, contain less terms. They are than the full Navier-Stokes equations, and they can be solved by means of downstream marching procedure. So moving toward elliptical equations. No real characteristic, no region of influence, no domain of dependence, information propagated everywhere, simultaneous solutions, jury problems, conditions specified over the whole boundary. Steady, supersonic, Inviscid flow. So similarly, incompressible Inviscid flow are exhibit elliptical behaviors. So boundary and initial conditions. So what is boundary conditions and what are basically initial conditions? So starting from boundary conditions. So moving towards boundary condition, a PDE with a special derivatives require boundary conditions. So whenever I am taking about a point which is in space, the required boundary is the boundary conditions, and while a PDE with a time derivative require an initial conditions. So boundary conditions mean defining the dependent variable and their dependent and their derivatives along the boundaries of the domain of the PDE. So initial condition means defining the time-dependent variable at some initial state. Dirichlet boundary condition, in which the dependent variables themselves are prescribed along the boundary domain boundary. So in Dirichlet boundary conditions, the dependent variables, either they are x or y, themselves are prescribed along the boundary domain boundary. Okay, and in case of von Neumann boundary conditions, normal gradient of dependent variables is prescribed along the boundary. So in Dirichlet, the dependent variables are prescribed, and in von Neumann, the normal gradient of the dependent variables are prescribed along the boundary. So Robin boundary conditions, in which the boundary conditions are a combination of Dirichlet and von Neumann type, and mixed boundary conditions, in which the certain portion of the boundary are defined as Dirichlet and while other are von Neumann. So these are the four types of boundary conditions. Now, in problem type, for example, equilibrium problem, marching problem, and marching problem without dissipation and this with dissipation. Equation type is elliptic, parabolic, and hyperbolic. So prototype equation is divergence gradient of phi equals to 0, and so this equals this one, and this is boundary conditions and marching initial and boundary conditions and initial and boundary conditions. So in equilibrium problem, we have closed domain. Marching problem dissipation needs open domain, and marching conditions with also dissipation also require open domain. They both are solutions are smooth, and this must be discontinuous. Classification of main categories of fluid flow. First is viscous, inviscid, and thin. Viscous basically is elliptic, and unsteady. Parabolic inviscid when Mach number is less than and when Mach number is greater than. So hyperbolic and unsteady must be hyperbolic, and thin shear layer steady flow must be parabolic, and unsteady must be parabolic also. Flow equations: steady, subsonic, and inviscid equations, and unsteady Navier-Stokes equation, mathematical behavior so elliptical, and solution algorithm solve all points simultaneously. When I am talking about steady Navier-Stokes equation, steady boundary layers, parabolized Viscous equation, unsteady thermal conditions, they are parabolic. So the solution algorithm involves space marching, space marching, and time marching. When I am talking about steady, supersonic inviscid equation and unsteady inviscid equation. So these are hyperbolic, and the steady, supersonic, inviscid are space marching, and unsteady are time marching. Flows involving both subsonic and supersonic flow regions, which is typically of compressible high speed. There is no need to deal with both elliptical and hyperbolic behavior at a time. However, an elliptical solution algorithm cannot deal with this supersonic flow region, while a steady hyperbolic solution algorithm is unsuitable for the subsonic one. So this is basically the physical behavior. So when subsonic flow, this is general. This is a reference point. This must be equal to C. This is 2C and this is 3C. Arranged disturbance for Mach number less than 1. So in first case, this is the region, and this must be 2C and 3C must be towards left. But there must be a V, 2V and 3V basically is the vertical or linear distance from center point. When sonic flow m equals to 0, so when m equals to 0, so the velocity must be equals to speed of light. So v equals to c. So in case of 2v, so it must be equals to c, and so 3v equals to 3c. And in case supersonic hyperbolic behavior, so information propagates downstream only and inside the Mach cone. So there is a Mach cone there. This is the Mach cone, and zone of action is there. This is basically zone of actions, and there's an angle that is known as alpha. The above is the zone of silence. So this is zone of action. The distance from this point, basically 3C to 2C is the V, and C to 3C is 2V, and from the center point to the 3C is the 3V. So these are the physical behavior of the supersonic, subsonic, and sonic flow. This is the end of the lecture today. This is detailed physical behavior and mathematical behavior of equation.